today's lesson we're going to cover how you determine if a molecule is polar or not. So that's called molecular polarity, and how it relates to the shape of the molecule. To properly understand this, we need to do a quick review of vectors. Those of you who already know what vectors are, you'll find this a breeze and fairly straightforward. If you're not familiar with vectors, we'll go over the basics of them, just so you can understand how they're applied to chemistry. So, what's a vector? A vector is some kind of quantity. There's lots of different types of vectors, but there's two key things that you need to have when describing a vector. One is a magnitude and the other is a direction. So here's some examples. You use vectors a lot in physics, but some that you might be familiar with. Velocity. Velocity, an example could be traveling at a speed of 10 meters per second. That's the magnitude. And the direction is north. Another one could be acceleration, 45 meters per second towards east. Another one is displacement, how much you've moved from one point to another when traveling, 150 meters west. You could even look at forces applied to different objects, 10 newtons northeast, and so on. The type of vector that we use in chemistry you've already seen before is a dipole. Dipoles are examples of vectors. They have a magnitude, which is determined by the electronegativity difference, and they have a direction, whichever way they're pointing. Remember, dipoles, when we show them on our molecular structures, are an arrow with a plus sign on the end. This end here is the partial positive end, and this end here is the partial negative end. So what we're going to do is look at how dipoles are arranged in three-dimensional molecules, or two-dimensional molecules if they're 2D, and then that will help us figure out the polarity of our molecules. But first we're going to still stick with vectors and what we can do with them. So when we look at three-dimensional structures, we have to draw on our dipoles, our vectors, and see what happens to them. So essentially what we're doing is drawing an example of a vector diagram. When you're just looking at regular vectors, you use a normal arrow, and the arrows have a head and a tail. So the tail is this end, if you're hearing that notation being used, and the head is up here. So when we look at vectors, they have two parts to them and we represent them by an arrow. What happens now if you want to add vectors? So we're going to do that with our molecules, but let's just take a step back and look at a simple example so we can try and put the pieces together if you're not sure about vectors. We have a dog. It's going to walk from point A to point B to point C, and we want to find out what its displacement is. So point A is over here. This is our starting point for the dog. We have our locations of A, B, and C. We also have some distances between the 3 points. Here, point C will be where the dog ends. Now, we already have the measurement. Between A and B is 4 meters. Between B and C is 3 meters, and for reference, we have the distance between A and C, which is 5 meters. So, dog starts walking. He's going from point A to point B. He's traveled 4 meters to the west. Then he continues on. He moves north, and he travels 3 meters and ends at his final destination. When we want to add vectors together, what we end up doing is taking where the vectors start and where they end for displacement. So here, if we want to find out what's the resultant vector when we add them together, what we need to do is go from our start location to our end, and if we measure it, it's going to go 5 meters, and the direction is northwest if we want to keep it that simple. So if we were to look at this on a north, south, east, west, just for reference. The displacement here, the dog is traveling northwest by 5 meters. This is our resultant vector arrow. So if this seems fairly straightforward to you, that's good. If you haven't seen this before, hopefully you can see how the displacement works. Now, there's one other thing that could happen. Let's add one extra stipulation to this example. So what if the dog now decides to go from point A to point B to point C, but then he goes back to point A? What if that happens? Let's mark that in a different color here. So the dog will go to point B, then he walks to point C, then he goes back to point A. So in this case, is there a resultant vector arrow, or what's the dog's displacement? Remember, when we're looking at displacement or looking at whether an arrow is left over, we have to look at the start and end point. In this case, the dog starts at A, but then he also ends at point A. So in this case, is there a displacement? No. In this case, there is no displacement. He started and ended at the same point. That can also happen with your vector arrows when you're adding them. So even though this example has nothing directly to do with what we're looking at with three-dimensional molecules and molecular polarity, the idea of looking at vector arrows and adding them together with our example of displacement is exactly what we're going to see when we decide on molecular polarity. So just a quick review, and if you need to spend some more time on this, I would recommend maybe spending 5 minutes reading through this if you need to. When we draw on arrows, those dipoles on our three-dimensional molecules, we have to come back and think about electronegativity. So just a quick review, the electronegativity difference happens between two elements. That dipole arrow we show with our plus sign there, it always points towards the more electronegative atom. And this helps us figure out bond type. So we know when that difference between two elements is approximately greater than 1.7, you'll find that that type of bond is ionic. Polar bond, it's the ones that are electrostatic, which are shown over here. Something positive and something negative holding those two elements together. Positive ion and negative ion. Remember, when we're dealing with molecular structure here, we're just dealing with covalent. So we're going to consider ones less than 1.7 down to 0. So depending on how the electrons are shared, if it's about 0.4, 0.5 to about 1.7, you get polar covalent bonds. And then below here, you get mostly covalent or non-polar covalent bonds. Going back and looking at some simple examples, we can start to understand how polarity is going to work. So all three of these are examples you would have seen in grade 11 and again in grade 12 with your diagrams. So if you want to pause and just practice drawing the Lewis diagrams for these three, go ahead and do that. And then we'll regroup and we'll have a look at how this all ties in with molecular polarity with dipoles. And if you don't have a periodic table handy, now might be a good time to pull one out, one that has the electronegativity scale on it. Okay, so if we draw these molecules, we have HCN, hydrogen cyanide. It should look like this. Oxygen is a small little molecule here. And carbon dioxide Should look something like this. Okay, so they're all three small molecules. If you look at their diagrams and you think about their shape, all three of them are linear. So all three are linear. What does this have to do with polarity? So not all of them are the same in terms of molecular polarity. First, what we're going to do is mark on the electronegativity values of the elements, and then we'll draw on the dipoles. So hydrogen is 2.2, carbon is 2.55, and nitrogen is 3.04. Okay, then we're going to look over here. Oxygen is 3.44, and over here, 3.44. And we've already got these values, so nice and easy to mark on. Okay, now that we've got the electronegativity values, we can add on any dipoles. So, dipoles always point towards the more electronegative atom. So between hydrogen and carbon, carbon's more electronegative, so its dipole is going to point towards carbon. Then we've got one, carbon and nitrogen. Nitrogen is more electronegative, so we've got a dipole that looks like this. Next, if we look at oxygen, because they're both exactly the same, there's no dipole here. The change in electronegativity is 0. This is a pure covalent bond. No dipoles here. Last, we've got carbon dioxide. Oxygen's more electronegative than carbon, so we're going to have two dipoles, one pointing each towards the oxygens like that. So up until this point, this is probably something that you did in grade 11. Draw on the dipoles, mark the electronegativity values, but it actually tells you a lot of information about the polarity of the overall molecule. So what happens now? First, let's look at oxygen. Here, there are no dipoles at all. If a molecule does not have any dipoles, we consider this molecule to be nonpolar. Nonpolar means there's no positive or negative end here. So here, nonpolar molecule. Nonpolar means that everything's pretty much symmetrical. All the bonds and electrons and atoms are arranged symmetrically. And you can see this by looking at this molecule. If you imagined cutting it in half right between that bond there, you would have two equal parts where the electrons are evenly distributed. But now let's take a look at what's going on with the other two. So if we take a look at hydrogen cyanide, we've got two dipoles. They're both pointing in the same direction. If we think about adding vectors or adding our dipoles, here we can add the two together. So here, two vector arrows, tip to tail, we're adding together. You'll get one big dipole left over. If you take a look over here, though, you've got two dipoles, but they're going to be equal and opposite to one another. So here, if we lined up the two vectors, let's say this is positive 1, and this is negative 1 approximately. When we add the two together, positive 1 and negative 1, that means 0. So here, our dipoles are going to cancel out. And over here, we get a net dipole resulting. So what's the difference between these two? Hydrogen cyanide and carbon dioxide both have bond dipoles, but they're different in magnitude and different in their directions. If the dipoles cancel out like we see here, Then we also get a case where we have a nonpolar molecule. There's no net dipole left over. So here, even though there are bond dipoles, since the dipoles cancel, nonpolar molecule. Again, it comes back to symmetry. If you imagine taking your molecule and chopping it in half. So right in the middle, this linear molecule, half would be where the carbon is. You'd have two equal parts on each side here. Oxygens are exactly the same bonding, same electron arrangement. So this molecule over here is symmetrical, same with the oxygen. And here, even though there's bond dipoles, overall the dipoles cancel and nothing's left. Different scenario over here though with the hydrogen cyanide. If you imagine chopping it in half where the carbon is, you won't have two equal parts to it. One part has hydrogen on one side and the other part has nitrogen on the other side. So this is non-symmetrical and we can see that there's a dipole left over. If a dipole is left over, then we have something called a polar molecule. So down here, as a summary note with what we're doing, if your dipoles do not cancel each other out, you get an overall molecular dipole remaining. So the overall molecular dipole we're referring to is this guy here. If that's what's left, then you get a polar molecule. And polar molecule means you'll have one end with a partial positive charge and one end with that partial negative charge. And what that does is it changes the properties of the molecule. You can have different interactions that take place between it, which will affect intermolecular forces, which we'll see in our next lesson. And those things affect things like melting point, boiling point, state, reactivity, and so on. So it does play a big role in the properties of molecules. All right, so now let's take all of our knowledge about vectors and reviewing electronegativity difference and dipoles and some of the simple examples we just saw. And now what we're going to do is apply it to VSEPR theory, and this is where it can get a little bit trickier. So if you were given any molecular structure that you've seen so far with all of the VSEPR diagrams, how do you figure out if that molecule is polar or nonpolar? So these are the steps you want to follow. 1. Draw a Lewis structure with the correct geometry and then identify each bond as being polar, meaning ones that have dipoles, or nonpolar, no dipoles. So make sure you go through all of VSEPR here. This is what you need. Okay. Then there are two cases to follow. And I would strongly suggest looking at these points in order because it will save you a lot of work in the end. So, how do you figure out if your molecule is nonpolar? First thing, if you have no polar bonds existing at all, this means no dipoles. If you have no dipoles at all anywhere in your molecule, like we just saw with the example with O2, oxygen, then you can say right away the molecule is nonpolar and you don't have to think about anything else. So it's nice and easy. This is only going to happen in a few cases or with smaller molecules. Next, if you don't have that case, let's say you do have some dipoles in your molecule. If you look at your molecule and you look at that central atom, so remember in VSEPR we have a central atom and then atoms are bonded around it. If that central atom has no lone pairs, no dots on it at all, and all of the groups are the same around it, so all of the atoms joined to the center are identical, that means the molecule is symmetrical and the molecule will be nonpolar. All of the dipoles will cancel out. And we'll go through how that works in a minute. Okay, so all of the groups are the same. This means all dipoles will cancel. Or you can think of symmetrical. Okay. If you want some other examples of what this means, these are 5 examples that fit with the 5 basic electron group geometries for VSEPR. Last case, what if there are dipoles? They're all symmetrical, but you might have different atoms around them, but if they end up being the same length, that can cancel. That's a very rare occurrence, but still possible. Now, if you've gone through step number 2 and gone through A, B, and C, and you don't meet any of those criteria, chances are you've got a polar molecule because you've got some dipoles left over and they don't cancel out. And essentially what this is going to mean is you have a non-symmetrical molecule. So what we'll do is walk through all of the different electron groups and a few different cases so you can see how the vector arrows, the dipoles, would work and how they might cancel or not cancel, and then we'll try out a couple of problems together. So starting off with 2 electron groups. This is your linear group. There's cases where they can be polar or nonpolar. So here if we look, here's our central atom, and there's no lone pairs on the central atom. And we look, there's 2 different elements on either side. We're going to assume that identical colors mean identical atoms. Here you have a case where you'll have a nonpolar molecule. If we wanted to pretend there were dipoles, you've got one to the left and right, both of same magnitude. Here the dipoles cancel, which means you've got a nonpolar case. Or if you want to look at it from symmetry, imagine you take that molecule and chop it in half. Do you have 2 equal parts to it? Definitely here. So you could also say this is a symmetrical molecule. You can have linear molecules that are polar, similar to the example we saw with hydrogen cyanide. So here you could have central atom and 2 others join. Let's say you've got 2 dipoles, different in magnitude but pointing in the same direction, or they could be opposite direction here. The point is here, since there are different elements, the dipoles won't cancel. And if you imagine looking at the molecule and chopping it in half, if you chop it in half, even though it's linear and will have 2 elements on the same side, they're not equal. Different colors mean different elements. You can see there's a single bond here and there's a triple bond here, so this is non-symmetrical. What happens when you start getting into the other groups? So now we're into 3 electron groups, which we know is trigonal planar. Trigonal planar has a couple of different options. We know trigonal planar can have our regular trigonal planar shape over here. So if that happens, then we could pretend that there are 3 dipoles. Let's say they all point outwards. Central atom with no lone pairs. All 3 identical atoms around the central atom. Here this will give you a nonpolar molecule. Here this is a little bit harder to see that this is symmetrical and that the dipoles would cancel. So let's imagine we add all of those dipoles together. So I've got one dipole that points up towards the north, and then I've got this one here that's pointing down, like this. And then if I take my third dipole and I add it tip to tail, it come back to where I started. Remember that example at the beginning of the lesson where we talked about the dog? The dog walks from point A to point B to point C or whatever that is. But in this case, the dog is going back to where he started. He started here and he ended here. Here, if we line up all of those dipole arrows, they start and finish at the same point. All of the dipoles here, when you add them, will cancel out, even though it's a little bit harder to see here. Now, what happens in a few other cases? You can have trigonal planar examples where you get polar molecules, which are these two over here. What if we just replace one or even two of the atoms and make them something different, different elements? Here you're going to have dipoles, but they're going to be different in magnitude here. This dipole here is different. So a different magnitude dipole won't cancel out, which will mean that the molecule will end up being polar. Or if we look at this example down here, if we walk through our steps of figuring out polarity, the first thing we did, if your molecule is going to be nonpolar, it can't have any lone pairs around it. That was one of the criteria that's there. So if we look at the central atom here, there are two equal and opposite bonds. But the problem is you've got this pair of electrons. There's nothing to eliminate that negative charge. So you've got some kind of net negative charge left around the central atom. So that molecule will also end up being nonpolar. When you start getting into the larger groups, there's more scenarios to consider. So we're going to walk through a few of the others with 4, 5, and 6 electron groups. So with 4 electron groups, you have a tetrahedral example. Again, hopefully you're starting to see some of the pattern now. Central atom, no lone pairs, 4 bonded groups, all to the same element. Here, this molecule will be nonpolar. There can be dipoles with all of them. If you add them in 3D, they will cancel out. What happens though if you have different atoms joined to the central atom? They're not all the same. Then the dipoles will be different lengths and one will not cancel out. Or what happens here when you have your trigonal pyramidal shape or your bent shape? Again, you're going to run into problems with those lone pairs. There's nothing to counteract the lone pairs. Here you've got 3 vectors pointing in 3D all over the place. These ones all won't cancel, plus you've got that. Here it might look like it's symmetrical when you cut it in half, but you can't counterbalance these two. It's not going to work for you. Let's say the dipole's pointed towards the central atom. They're going to make one big dipole that points up towards the center as all of that electronegativity is pulled around the oxygen. Plus, you've got those 2 pairs of electrons and they can't be canceled out. Now, if you get into the larger groups, remembering their structure and trying to visualize that can be helpful. So these 2 are examples of nonpolar molecules in the trigonal bipyramidal family. First, our trigonal bipyramidal shape here, central atom, all 5 bonds to the same element, no lone pairs. How does this one cancel out? So, remember our North Pole, South Pole analogy. North Pole and South Pole are lined up in a line. 2 equal and opposite dipoles will cancel one another. So these 2 dipoles here cancel each other out. Then when you look at around the center, that's the equator, you have 3 groups around the equator. But remember, they're all in the same plane. Around the central here, remember, takes on your trigonal planar arrangement. And we just said for trigonal planar arrangement, if all 3 are bonded to the same element. There'll be three dipoles, but all three of these will cancel out when we line all of the dipoles up. So that's why this one ends up being nonpolar. North and south pole cancel, and all three around the center here, since they all lie flat in the same plane with the same magnitude, they will cancel out. Same kind of idea applies here. What if you have the linear molecular shape that falls within this family? Similar idea, you've got your north and south pole with dipoles. They'll cancel each other out. And then you do have electron pairs around the center, but here remember around the center they are arranged in the same manner as these three bonded groups. Even though they're all electron groups, they're still going to spread out 120 degrees from one another around that equator plane. And these three will also end up canceling out. So this is one that might be considered an exception to the rules that we went through at the beginning. Now, if you were to change the different atoms that are joined here, then you would have a different scenario. So here are a few examples where you could end up with polar for trigonal bipyramidal. It doesn't encompass all of them, but just to give you a variety. So let's say you switch up even just one or two or three of the elements around the central atom in trigonal bipyramidal shape. The dipoles will not cancel, and this will end up being polar. This is the problem over here. What about if you have your seesaw configuration or your T-shape configuration? These two dipoles might cancel, but then you're left with these two plus this lone pair. So here you won't have all of the dipoles canceling out. Same idea with T-shape. You might have two dipoles in the same plane that could cancel, these two. But what happens to this one guy here? And what about these lone pairs? There's nothing to counterbalance them or make that molecule symmetrical in terms of the electron distribution. So it's going to end up being polar as well. Last but not least, you've got your octahedral group. So what are some examples of non-polar ones? Here are a couple. So again, let's try and remember. North pole, south pole, they'll cancel. And then you've got four around the equator. Remember, around the equator, they're all 90 degrees to one another, so they're directly perpendicular. So that means these two are in a straight line with one another. They're going to cancel out. And then these other two, they are, remember, perpendicular to their neighbors. They also line up in a straight line. So here, they cancel out. So here, all dipoles cancel. Here's our example with Vesper. Remember, this shape is your square planar shape. It looks like a plus, or it lies flat. So again, this is what's happening around the equator over here. You've got two bonds in a straight line, equal and opposite dipoles or forces. They cancel. These two are also in a straight line in terms of forces, equal and opposite. They cancel. And then you've got two pairs of electrons. They're taking the place of the north and south pole. So this one here is pointing north. This one here is pointing south. Equal and opposite. They will cancel each other out here. So you've got dipoles that cancel and the pairs of electrons cancel. Here are a couple more just to show you a few more variety. And again, with octahedral, you can have a few more combinations. But if you replace any one of the atoms with a different element, that will change the dipole length, which will make it polar. It won't cancel out. You might get these ones canceling out in the equator plane, but that when it comes here, you've got this tiny dipole and a big dipole around here. You're going to have a problem with that dipole not canceling out. You're going to have some kind of dipole left. Or over here, when we look at our square planar shape, or sorry, square pyramidal shape. Again, these guys might cancel. These guys will cancel. The problem is, again, lone pair, plus you've got a dipole that can lie in that plane here. So this one here in the center will not cancel out. So now that we've looked at vectors, vector addition, dipoles, different possibilities for the 6 electrons, 5 electrons, 4 electrons, 3 electrons, 2 electrons arrangements, let's look at some examples together to put this together. So the questions will ask you very simply, are these molecules polar or nonpolar? So what you're going to do first is draw out the molecule according to Vesper and identify its geometry, group, and shape. So since we've already covered Vesper, for each one of these examples, I would go ahead and draw the molecule, identify the electron group and actual molecular shape. And then when you're ready to check, we'll start walking through the examples together. But this is another opportunity where you can practice a bit more of your Vesper names and diagrams. So pause. When you're ready, we'll walk through these examples together. All right. So when we get to methane, which is CH4, if you did your first Lewis structure sketch in 2D, it might look something like this. Around the central atom, you have 4 electron groups. So this is tetrahedral electron group geometry, and its actual shape is also tetrahedral. In 3D, we know that our molecule will look something like this. Okay, so when we look at this, we've got carbon. Carbon is bonded to 4 atoms, no lone pairs here, and all of the atoms are identical. There are dipoles, and they do point towards the carbon, but if we were to add them in 3D here, they all cancel. So here we have an example of a symmetrical molecule. Central atom, no lone pairs, all bonded pairs, all to the same atom. This one we can say is nonpolar. Let's try another one. So hopefully you've drawn the next example. ICl3. So 28 electrons. Let's make a sketch. ICl, Cl, Cl. When we look at these, we've got our electrons on there. So here, when we take a look, we've got a central atom. There are 1, 2, 3, 4, 5 electron groups, which means it's trigonal bipyramidal. The actual shape, again, determined by the bonds. 3 bonded pairs, 2 lone pairs, means we have a T shape. So if we want to look at this more accurately, even though I sketched it, it still looks like a T shape. I, Cl, Cl, Cl. Drawing this so it does look like the T shape with those 90-degree bond angles. And we've got those lone pairs on there. So going through our criteria, when we look at the molecule, if we draw on the dipoles, there are definitely dipoles here. Okay, so doesn't meet criteria A, no dipoles. We have dipoles. Criteria B, Are there any lone pairs? Yes. So that won't fit criteria B when we look at our steps. If they were all bonded pairs, then that would fit criteria B. It doesn't. But here we've got 3 bonded pairs and 2 lone pairs. So here, our problem is all of the dipoles won't cancel. These two here, the ones that are lining up, these 2 dipoles will cancel. The problem is this one down here won't cancel. And then you've got the lone pairs here that are not going to cancel. So here in this example, dipoles don't cancel. It's non-symmetrical. In its electron distribution. And because of those two things here, we have a polar molecule. So yes, all that work to figure out whether it's polar or not, but it combines a lot of concepts together. Let's take a look at a few more. So next one was I3 negative 1. So here, if we're going to draw this one out, and I'm going to draw this one with the right geometry right away. So here, this one belongs to the 5 electron group geometry. 1, 2 bonded pairs, 1, 2, 3 lone pairs. What is its actual shape, molecular shape? 2 bonded pairs, 3 lone pairs means linear. And now I can look for any dipoles and see what's going on. So, since all 3 of these atoms are the same, they all have the same electronegativity value. Are there any dipoles here? No. No dipoles. So between iodines, there are no dipoles, so they cancel out. Then we've got 3 lone pairs around the center. The 3 lone pairs, though, remember, they are arranged in a trigonal planar configuration. And this is around the equator of your shape. So even though there are 3 lone pairs, since their trigonal planar arrangement around that equatorial plane, these ones will cancel out. So no dipoles, and those 3 lone pairs around the central plane, the equatorial plane, cancel. Since both of those criteria are met, here we're going to have a non-polar molecule. Let's try one more to finish it off. Again, if you haven't tried one, I would recommend trying this one, just again so you have a chance to practice and can check. So here, we're looking at 42 electrons in our diagram. Let's make a quick sketch. Bromine, fluorine, 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 fluorine. And we're going to put our electrons around. That's 40. And then 42 means we have a lone pair. So when I look here, 1, 2, 3, 4. Oh, we're forgetting one. When I'm counting, that makes more sense. 8 times 5 is 40, plus 2 is 42. So when I look here, I've got 1, 2, 3, 4, 5 bonded pairs and 1 lone pair. That means 6 electron group family. So I know I'm dealing with octahedral. With this arrangement, 5 bonded pairs and 1 lone pair, I've got my square pyramidal shape. And when I draw this more accurately in 3D, this helps me understand the dipole arrangement. There we go. Now we've got it all in. So again, remember we've got octahedral shape. These ones are around the equator. They're all 90 degrees to one another. So even though I'm not the best artist, these two fluorines are in a straight line. Those two dipoles will cancel. These two, again, are in a straight line, equal and opposite dipoles. They will cancel. But then you're left with the problem here. You've got this lone pair down here, and you've got a dipole that points up towards that fluorine. This is your north pole, this is your south pole. They are not equal and opposite to one another, so here you'll be left with some sort of dipole that's left over. So here, because of that, all dipoles don't cancel. So this is a polar molecule. So here you can see the importance of knowing your Lewis diagrams, your VSEPR diagrams, and having an understanding of dipoles and how they're arranged in 3D based on those shapes helps you figure out molecular polarity. So make sure you get lots of practice with this. Again, if you need help with the actual VSEPR shapes, keep working on those first, and then try back when you're ready to practice with these ones.